I'm indeed Kostya Serebryany from Google. My team is called Dynamic Testing Tools, and we're not the security guys, we're the compiler guys. We're doing the tools for the security guys. Interesting thing up there. Today, I will tell you about 3 related things. First, you will know about so-called sanitizers or dynamic analysis tools for C++ code. Second, I will tell you about the fuzzing tools we developed and we use. And last but not least, I will mention hardening techniques that we developed at Google for C++. My hope is that many of you will start using these tools first thing tomorrow morning when you get to your desktop. I've joined Google about 8.5 years ago. And soon after that, we started using and deploying Valgrind dynamic analysis tool on our C++ code base, which at that time was already many tens of millions of lines of code. By the way, how many of you have heard about Valgrind? Good, good. So Valgrind is based on binary translation, and it's one of the weaknesses of this tool. Still, we found lots of bugs, like many hundreds of bugs, maybe even thousands. But the weakness of the tool, which is a huge CPU overhead, did not allow us to move to a situation where we would like to see ourselves, which is other developers using the tools on their tests without our intervention. We tried hard. We found lots of interesting bugs. The developers were happy to fix them, but they were not eager to use the tools themselves. The reason, just one, too slow. So after 4 years of trying to deploy Valgrind wider than it was deployed, we started developing our own tools, and the family of tools we developed we call the Sanitizers. How many of you have heard about the Sanitizers in the C++ context? That's too few. So I hope, well, how many of you have heard about them now? Good. By the time we started the Sanitizers, we already have over 100 million of lines, well, 100 million of lines of C++ code. The new tools are based on compile instrumentation. And today, most of these tools are available in the 2 major open source compilers, LLVM and GCC. There are 4 major tools. ASAN stands for AddressSanitizer. It detects things like use after free buffer overflows, memory leaks, and all the traditional suspects. TSAN, Thread Sanitizer, finds concurrency bugs, which mostly means data erasers and deadlocks. The third tool, Memory Sanitizer, finds a single type of bugs today, which is uses of uninitialized memory. And last but not least, UBSAN. UB stands for undefined behavior, and it finds that. More or less all kinds of other undefined behavior in C and C++. Let me give you just one example of just one of these tools. The C++ example on this slide is the simplest I could come up with for use after free bug. Probably most of you are familiar with this kind of bug. You allocate memory, then you deallocate memory, and then you continue using this memory for some purposes. If you want to find this bug with AddressSanitizer, all you need is to compile your application with a single special switch. And again, this switch is available in modern Clang and in modern GCC. If the bug happens at runtime, and this is a dynamic tool, it actually needs the bug to happen at runtime, the application will print a lot of descriptive text saying what kind of bug happened, what is the address, what is the stack trace of the bug, what is the stack trace of allocation, deallocation, etc. And after that, it will immediately trap. The sanitizers are fast. For most of these tools, the typical slowdown is about 2x. Compare it with Valgrind, 20x. So we were able to run almost all of the unit tests in our huge code base with the sanitizers. Little bit more details about the Chromium. which is an open source project on which the Google Chrome browser is based. Chromium is about 10 million of lines of C++ and a little bit of C code. And the unit tests are a very important part of this source base. We have unit tests for every single bit of our own code base. Not necessary for third-party libraries that we're using, but at least for our own code base. And with the sanitizers, we were able to run all the unit tests for almost every commit. And we have multiple commits every day. So it means that if we find a bug, a new regression, we can report it, revert it, or fix it within a few hours, not within a few days or weeks, as we had before. So we found hundreds of bugs this way, both old bugs that were there for years and regressions. But the test coverage is never perfect. It is actually usually quite bad, but if you think about targets that the bad guys would look at, I would say that test coverage is very poor, almost always. So the bugs still slip into production. And this brings me to the second part of my talk about fuzzing. Several people mentioned fuzzing already, and this talk is too small to explain fuzzing in more detail, but I will try to do it in one sentence. Fuzzing is a huge family of different techniques which have the same goal. We need to generate lots of test inputs for the application, for the API and the test, with the goal to increase the code coverage and in the hope to make the code misbehave. And if you make the code misbehave, you found the bug, you reached your final goal. And if you want to find this misbehavior more efficiently, it's a good idea to couple fuzzing and one of the sanitizers. At Google, there are several teams that develop and use several different frameworks or pieces of infrastructure that run many hundreds of fuzzers. Several thousands of CPU cores fuzzing something every minute. And with fuzzing, we found at least an order of magnitude more bugs than with the unit tests. Maybe actually 2 orders of magnitude. In Chromium alone, we found at least 5,000 bugs, maybe more. And in FFmpeg package of video codecs, we found more than 1,000 bugs. But I want to dive deeper into one specific fuzzing tool which my team develops. The tool is called libFuzzer, and it performs guided fuzzing for other libraries or for APIs. And this slide explains how to use this tool. So first of all, if you're testing something, come up with the initial test suite for the thing you are testing. In some cases, this initial test corpus could be empty, but the more inputs you provide, the easier it will be for the fuzzer. The next step is to implement what we call a target function. Target function is a simple C function that takes an array of bytes as a parameter and does something interesting with these bytes. Parsing some data format, for example. The next step is to build your library or API and the target function with a special compiler switch. Today it's available only in LLVM. I hope we'll see it in GCC at some point. You may also, and you're encouraged also, to add one of the sanitizers to get better results, to find bugs quickly and with more detailed. And then you just run this application on multiple CPUs. The test corpus will grow. The test units will be written back on disk, so you will have more test inputs as the fuzzer runs. The bugs will be reported to STDR, and the reproducer inputs that trigger bugs will be also written on disk. Let me show you an example. FreeType library is a font rendering library that is used on every Android phone, that is used by Chromium, and in many other applications. And this target function calls the FreeType API that opens a font in memory and parses it. That's it, 5 lines of code. Even though the target function is very simple, we were able to find several dozens of bugs in free type. Some of the bugs are just stability bugs, but several may have security implications, like buffer overflows, signed integer overflows, or leaks may lead. Memory leaks typically are not considered as security bugs, but they are because they can lead to DOS attacks. Let me show you something even more relevant for security conference. This is a target function for OpenSSL. We have a little bit more code here, but it's all boilerplate. If you know how OpenSSL works, you can write it with closed eyes. And in this target function, we're testing a single API function of OpenSSL, not the entire OpenSSL. Does this function ring a bell to anyone? Come on, anyone? So this is the function where the heartbleed bug was found a couple of years ago. How many of you believe me that I can find heartbleed from scratch before the end of this talk? So I'm running the fuzzer without any initial corpus. It knows nothing about OpenSSL. It has no clue about the data format. All it does, it tries to put some random bytes, mutate the existing tests, and if the mutation is good, based on the feedback we get from the compiler, we add this mutation back to the corpus. I haven't finished talking about this when the fuzzer coupled with AddressSanitizer found the bug. So it is a heap buffer overflow, as you can see on the screen. We were reading 43,000 bytes out from somewhere, and the second frame in the stack is something process heartbeat. I have no clue what that is. I am not an OpenSSL expert, but it sounds like heartbleed. Some of you may tell me, hey, that's old news. Of course heartbleed was found with fuzzing. We all know this. That's not my point. My point is that it is nowadays so simple to make a fuzzer for OpenSSL, and it will find this bug so fast. You've seen a few seconds on this laptop. So there is no reason not to use fuzzing. This is a screenshot of code search of the Chromium project, all public, all open source. And we're trying to add fuzzers for every interesting API that Chromium uses. That includes the Chromium API, the Chromium proper APIs, and the APIs from third parties that Chromium uses. We've made libFuzzer very simple to use for everyone, and we're trying to make it super easy for the Chromium developers and for other developers at Google as well. I believe that fuzzing, not just libFuzzer, but fuzzing as a technique, should become a key feature of everyone's testing process, just like unit tests are today. But fuzzing is not enough. And we know it at least because of two things. First, every time we add a new fuzzer to our testing process, we find new bugs. It means that the existing fuzzers are not enough. But we also sometimes learn about bugs that actually slipped into production. And sometimes we know about it in bad ways. This leads me to the last part of my talk, which is about code hardening. I will describe two threats and two mitigations for these threats. Threat number one is traditional memory corruption, when the bad guys overwrite your function pointer or a virtual pointer with something they control. This is not a theoretical problem. We've seen it in the wild many times. This is an oversimplified example of the bug in question. Suppose you have a buffer somewhere, which is followed by a function pointer. And if your code has a buffer overflow, where there is a chance that the function pointer will be overwritten with a pointer to some bad code, it doesn't have to be bad code, it's just the code that the attacker can use for their purposes. If you build the application in a regular way, the bad code will actually be executed if the attacker is killed. If you add a couple of compiler switches to build the application, the key one is fsanitize equals to CFI. CFI stands for control flow integrity. Your application will immediately trap while attempting to execute this incorrect address. There is also a diagnostic mode in this compiler feature, which will not trap immediately, but will give you a detailed explanation of what has happened. How does this work, in short? The compiler statically computes the exact set of targets that are allowed for every given call site. Today, this requires so-called link time optimization, which means that the compiler sees the entire application as a whole, as if we were compiling it as a single C++ file. And once we have computed this allowed check, we insert a constant time checking code before every call site. So the concept of CFI and the way of doing this has been known for a while, but what we have achieved is the speed of this check. Our check requires at most single memory load per indirect call, or sometimes not at all. The second threat is also quite popular, a stack buffer overflow overwriting a return address on the stack, again by something that the bad guys control. And again, this is not theoretical, we've seen it in a few cases. This kind of mitigation is even simpler. And so the example is even simpler. Suppose you have a buffer on stack, and there is an overflow that may corrupt data behind the buffer. And so it happens that if you compute the offset correctly, you will corrupt the return address. And instead of returning to the caller, you will execute the code that the bad guys want you to execute. So if you compile in the regular way, this will happen. If you compile with fsanitize safe stack, nothing will happen. So is it good or bad? It is better than allowing the bad guys to execute their code. We do not detect the bug, but we do not allow the exploit. How does this work? Safe stack uses a well-known concept of shadow stack, which is a separate memory region of the same size as the original stack of every thread. At compile time, we place all local variables that are potential targets for buffer overflows on this shadow stack. And if a buffer overflow happens, some data is corrupt somewhere, but there is no chance the return address will be affected. This technique could be combined with stack cookies that have been mentioned on this conference a few times, although frankly, I don't see any reason for this. Both mitigation techniques I've mentioned are not exactly free. Each of them incurs 1 or 2% CPU overhead and even greater code size. But if you have an application that is security sensitive, this is a good price to pay. To summarize my talk, and as many mentioned here already, security could be either in-depth or none at all. And if you want to get some security, you should be using the sanitizers, fuzzers, and code hardening techniques, and everything else, of course, as well. And slide with index -1. We also have all these tools for the Linux kernel, not just for the user space. And this is a you cannot really see it here. It is a subset of bugs in the Linux kernel we found during the last 3 months. As you maybe can see, use after freeze are quite popular features of the Linux kernel. All of the tools I've discussed are open source and public, and the documentation is available online. Thank you.